In this discussion video, we will do some practice true-false limit questions. So I want to look at problem number 9, parts A, C, and D from worksheet 2, which says true or false. If it's true, show why. If it's false, give a counterexample. And I want to begin by having you try part A, which says if the limit as x approaches 3 of f of x is 2, then the limit as x approaches 3 from the right of f of x is 2. So pause the video and try this one for a minute. 4, 3, 2, 1, pause it and try part A for a minute. Alright, so hopefully you've paused it and tried this one for about a minute. So we saw something pretty similar to this in our lectures, but in the reverse order. So what we're given here, the if portion is what we're given, is that the limit as x approaches 3 of our function is 2. So this overall limit, or this two-sided limit, is 2. So since that's the case, since the limit as x approaches 3 of our function equals 2, this means both of the one-sided limits need to be equal to 2. Both one-sided limits, I'll abbreviate lims, equal 2. So if I think about my conclusion here, that's the then part of the statement. This is the conclusion. The conclusion is one of those one-sided limits. It's the one from the right. So based off of what I now know, in particular, because both of the one-sided limits equal 2, in particular, this implies that the limit as x approaches 2 from, or sorry, it's approaching 3, my mistake there, approaching 3 from the right of my function, that equals 2. So our conclusion holds, and that makes this statement true. Maybe let me put true at the front here. It is true. Alrighty. I didn't ask you to pause the video to try part B, but part B is a really similar problem to what we did in lecture. So I just want to make a note of that. We did almost this exact problem in lecture for part B. Just the numbers were different in lecture. So this would be a good practice problem to try as well, although I won't talk about it here in discussion. Next, I want to give you a combined 7 minutes to try parts C and D. So I would say a good breakdown is give yourself 3 minutes to try C. Even if you don't finish, that's okay. At that point, I want you to move on and try part D for about 4 minutes. 4, 3, 2, 1, pause the video. Pause the video and try these for a combined 7 minutes. So let's talk about part C together, but hopefully you paused it and really tried this for 3 minutes. If not, I'd highly encourage you to pause the video and try these. It's super important to go through the process of thinking about what the key ideas are and assessing how well you're able to apply those concepts to tackle new questions like this. Alright, so this says if the limit as x approaches a of g of x and the limit as x approaches a of f of x over g of x both exist, then the limit as x approaches a of f of x exists. So the given part is the if portion of the statement. That's the fact that these two limits exist. Okay, and because it tells me that they exist, let's just call those limits something. Let's let the limit as x approaches a of f of x, let's let that be L1. And let's let the limit as x approaches a of f of x over g of x equal L2. And L1 and L2, these are finite numbers. And I know that because it tells me that these limits are supposed to exist. That means that their outputs, these y values, are approaching finite numbers. Alright, so the setup of this question reminds me of the limit laws. It reminds me of limit laws in that it tells me that there are these two limits that exist, and it's asking, well, does this other limit exist? Well, if I can form this function, f of x, by doing something to g of x and f of x over g of x, somehow combining them, like dividing them or adding them, I'm going to be in business. And it turns out what works is multiplying them. So by the multiplication limit law, if we form the limit as x approaches a of the first function g of x times the second function, which is f of x over g of x, the limit law says, okay, because both of those individual limits exist, this is going to be equal to the limit as x approaches a of the first function, g of x, times the limit as x approaches a of the next function, f of x over g of x. I can only say that because both of these limits exist. Okay, and if I simplify the left-hand side, it's the limit as x approaches a of the g of x's cancel, and I get f of x. And on the right, the limit as x approaches a of g of x. Now, whoops, I realized I miswrote something. Up here, I had written f of x. This should have said g of x. Right, because in the original problem, I was given the limit of g of x. So I should be writing g of x here. Alrighty, so the limit as x approaches a of g of x, this should be L1 times, and this other limit is L2. So we just got that the limit as x approaches a of f of x is equal to L1 times L2. And this is a single finite number, which means, thus, the limit that we cared about as x approaches a of f of x, that limit exists. That limit exists, and that is what we were hoping to show. So that makes this a true statement. All right, and now let's move on to part D of this question. So part D, I think this is probably the most challenging out of these three. It says if the limit as x approaches a of f of x does not exist, D and E, then the limit as x approaches a of the absolute value of f of x does not exist. So with more challenging questions that we talk about in our class, and I think that this is an example of that, it's going to be natural to think about it for a while, get stuck, struggle with it, and then use our resources for help to ask questions, like maybe come to office hours or to SLC tutoring to ask for help with it. And then think about it some more after that. Maybe sleep on it, think about it more the next day, and then some ideas will start to form. That is very common as we're adjusting to the expectations of college-level math courses. Okay, so let's see if we can start to break this one down. So the first thing I want to just recall is, well, if I have a function and then I take the absolute value of that function, how does it affect the graph? So I want to recall that if y equals f of x, and I just form a graph of some function, and maybe the graph looks like this, goes down, and goes up, goes down a little bit, and then maybe goes up again. And let's just say that it crosses the x-axis at -4, and then at +1. And then I'm going to form y equals the absolute value of f of x. Maybe I give myself a little bit too much room initially. All right, so there we go. I just adjusted it to give myself a little bit more room to draw this graph. What happens when I go from this original graph to the absolute value graph is, the absolute value graph is going to take the values that we get out of this function, the y values. And when they're positive, when they're non-negative, the absolute value doesn't do anything to them. It just keeps them the same. So from 1 onwards, the y values are all non-negative, so those will all look the same. And then from before -4, all the y values are non-negative, so those y values should stay the same. But any output, any y value that is negative, and that is this part of the graph, the absolute value is going to make them positive. It's going to make them positive, and that's going to flip them above the x-axis. So that part of the graph will look like this. So that's what putting an absolute value on a function does to its graph. It's going to flip the parts that are below the x-axis up above it. So at this point, I'm going to give you a hint, which is I'm actually going to tell you what the answer is. This is false. And now I'm going to ask you to pause the video and see if you can now think of an example of a function where when you draw it, just try to draw a picture where the limit of as x approaches a of that function does not exist. But when you take the absolute value and you look at the absolute value graph, that one will exist. Pause it for 2 minutes to try that. 4, 3, 2, 1, pause. pause the video for 2 minutes to try that. This is an opportunity to get practice getting a hint and spending more time thinking about that hint after we initially made some progress. Alrighty, let's talk about it more and let's see if we can wrap this up. So let's let y equal f of x be, I'm going to draw a graph below, be the below function. So I need a function where the limit in the original graph is going to be d and e, but when I absolute value it, it's going to exist. So I'm going to draw two pictures. One is going to be the original function, one is going to be the absolute value function. So here I will draw the absolute value. Okay, so when I absolute value it, the part that's below the x-axis is going to flip up. So maybe let's try to do something where I have a function, maybe this is a y value of 1, and it's like that. And then maybe over here I'll put something that's negative, but I'd like it so that when it flips up, the limit exists. And I can do that if I make this part go to -1. Maybe let's just make it horizontal for simplicity. And now when I absolute value it, this part of the graph stays the same because those y values are already not negative. But these y values are negative. They are going to get flipped up. They're going to get flipped up to be at +1. So in my picture now, the limit as x approaches 0 of f of x in this original graph, this one definitely is d and e because the left and right hand limits are different. But the limit as x approaches 0 of the absolute value graph, that equals 1. It's 1 from both sides, which means that limit exists. So we have just come up with a counterexample, and that shows this one's false.